Sorry. Good afternoon, everybody. Welcome to our EE Distinguished Lecture. My name is Peter Kinget. I'm currently serving as the chair of the Electrical Engineering Department. It's my distinct honor to introduce our speaker today, Professor Rick Osgood. It's really nice to have all of you here for this talk by our distinguished colleague. Going through all Rick's accomplishments and all his accolades would take way too long, and I think we're all here to listen to Rick instead. But let me point out a few key accomplishments. So Rick has been at Columbia since 1992 and has not run one group, but actually two research groups. One on the fundamentals of light surface interactions and one on photonic devices. He has published over 500 papers spanning from fundamental science to cutting-edge technology. Rick's research contributions are numerous, broad, they're in optics and in basic surface science, and for this he was recognized with fellow status in several professional societies. For his groundbreaking work on laser microchemistry, he received the R.W. Wood Award from the Optical Society of America. Several of the advances that Rick accomplished with his students bridged the gap between basic science and technology in laser chemical processing of surfaces, integrated optics, software for the design of integrated optics, crystal ion slicing, to just name a few. Because of this, Rick's contributions have led to successful commercial ventures such as RSoft, which designs software for integrated optics. Rick has been instrumental in the truly remarkable growth of our school in recent decades. For example, he was a driving force in establishing and leading the Columbia Center for Integrated Science and Engineering, which has been very important in fostering collaborations between science and engineering at Columbia, and which also helped lay the foundation for the recent Columbia Nano Initiative. He was a key member of several prestigious government committees on policy in science and technology, and he also had a significant impact at Brookhaven National Laboratory, where he was an associate laboratory director from 2000 to 2002, and he established the Center for Functional Nanomaterials. He has also been very helpful in establishing collaborations between Columbia and Brookhaven. In the past year, I've personally gotten to know Rick better. I knew that he had been an exemplary professor, a superb colleague, but I've been even more impressed by Rick's deep dedication to his student. He can really be an example to all of us as to how dedicated he has been to his 60 or over 60 PhD students. Many of them are here today, through all their time at Columbia and also later in their careers. Rick will now give us his personal perspective on laser research and the evolution of science in our time. I hope you all join me in welcoming Rick to the stage.
Hey, it's great to be here. I've been away for quite a bit recently, but you come here and memories flow across your brain and you remember things. One thing I remembered about this room, there's two things very key. One is, one time there was a big meeting we had and it was about 40 degrees inside. Everybody was freezing to death. A second one was we had a wonderful professor from MIT come down. He was all excited and somebody asked him a question and he grabbed a magic marker and wrote all over the screen here, which was another wonderful thing. Maybe another way to introduce the thing is to point out that there's not just one Richard Osgood in this room, but there's two more, my grandson and my son. Okay, so I thought I'd just point that out as a happy picture. Okay, today I'm going to present the Armstrong lecture, and I want to do it in the way that I think could make a difference to people here. So I'm going to try to help people understand how I developed my scientific career and life and to give some of the pointers to you, and I'm going to illustrate it with some examples, some science examples out of that. I start off just with a picture here of the good Professor Armstrong, an incredible genius, and a good example for us all interested in science. I also point out that most of his life, I think he did most of his research all by himself with his own hands, and how different it is nowadays with large groups and things like that. Okay, so the title of my talk will be Laser Research and the Evolution of Science in Our Time. So I'm trying to show a dynamic picture here of how science in the United States evolved during the decades which I've been involved in it. By the way, 52 years. I counted them a lot of times. It's 52 years I've been in science. So it's a long time. Another title for this is Looking for New Science, Finding New Applications. And I think that's maybe the way that my own heart beats. I love new science, and I'm very interested in new applications, particularly where they can help people and translate those ideas on. Basically, I'm going to be talking about physical science, of course, and with one exception, I've done no medical science at all. The one exception was zapping guinea pigs at Lincoln Labs when nobody knew it. So that was, we'll get to that in a minute, okay? Okay, now I point out that I've done most of my work, and most people don't, a lot of the students are new and everything. I started out at Wright-Patterson Air Force Base in Ohio, and I took a little picture. It's not so clear to see here, but it's bombers on a runway, and this was early 40s, and I guess I'm a child of the 40s when you really get down to it. And after that, I went to MIT in physics, MIT Lincoln Laboratory, Columbia, and then I did a stint at Brookhaven National Laboratories as a director, as Peter said, and back to Columbia. It's an interesting thing to point out. I want to point out that my introduction to science at Wright-Patterson Air Force Base, I was in a new kind of program they had, and I had, most of the time you have a nice professor there or a postdoc you can talk to. Well, I went into a lab, and the guy said, "That's it," and he walked out. And so I ended up having to try to figure out what the heck to do on lasers, of which I knew nothing at the time. And it was a wonderful experience, and it teaches you how you can do things on your own. Since that time, I have a number of different kinds of players who've worked with me, senior researchers. By the way, I may leave people's names out. I obviously don't mean to do that. It's an accident if it happens, okay? But senior researchers here, in fact, I just see one right now, Julian Chen's name should be up there as having done an awful lot of work with me over the years and interacted with me while he's done such beautiful work in solar cell technology and so forth. We also have a lot of students, as was pointed out, and administrators. Now, I think administrators, people are bored about administration. Oh my God, it's terrible, who has to do it? But in fact, the administrative load on people as you go forward in time has increased dramatically. So Armstrong probably had very little administration he was worried about. When you get up into the mid-time when I was there, it started to get fast and thick, and then finally it's really very heavy right now. Svetlana helped me most recently, Teresa initially, and many other people in between. Grace, turns out, played a huge role in getting the nanocenter at Brookhaven. She played a major role in doing that. I could take any one list here and go through it, and you'd see all the diverse things that happens to students when they graduate. People are lawyers. People are real lawyers, that is to say, got nothing to do with technology. People are wealthy businessmen in China. People are professors. People are just starting small companies. Very, very interesting evolution over time. Okay, so I'd like to organize my talk then sort of in a temporal way. Okay? So I'd like to start off with different types of scientific interest at the time that these at the time that is indicated here in red, and go through each one of these and try to explain what it means. So what these represent is some image, some idea which has been involved at the time, what science found exciting at the time, what people funded big programs for, and what was of interest. Now, as I say, I've left some areas out, of course, so I'm talking about physical science and the ones I'm in. So we'll go through each of these. So I'm going to go through, and each one of these things will be repeated, and you'll see where we are in the talk as we go through it. Okay? So let's start, but there's a little bit of other things to happen. First of all, that's a big area I just showed there, but our groups was mainly control of coherent light at or near surfaces. In other words, we were interested in light near another surface to see where it was going. Spectroscopic, chemistry, what have you, okay? That was the focus there. We might want to just reflect back for those of you who are not working in lasers right now. But typically a laser consists of resonator, medium, active medium, and another resonator right here, or another mirror right here, I should say. And basically, this, for example, the laser medium, the whole issue there is to try to prepare that medium so that one atomic level is populated very highly, whereas another level, which is connected to it by an optical transition, is populated in a very small way. So you have gain. Okay, and so this is a province of a lot of early physics work right here, as we'll talk about in a second. But you're interested in things like collisions, which the atoms hit each other, or walls, quantum effects, line shapes. We're also interested in the optics a little bit. How does this cavity be formed? Is it two planar mirrors as shown here, or is there curvature? Can you use other more subtle things? The answer is yes. And then finally, what about surface interactions? What can you do on a surface with a lens? Because after all, this is a very clean and very pure light that enables you to hit the surface and cause, let's say, a reaction, or to photoemit from the surface, both of which come about here. Now, Columbia has played an enormous role in this. So I put down the founding fathers here, and I put down over here a kind of the early statement of, or not the early statement, but a statement as to what appeared on their Nobel Prize thing. So they're interested in quantum. This point was Towns and Basov, and I didn't put down here Prokhorov for a reason. Actually, we're interested in looking at amplification, gain, non-equilibrium situations in medium, which then was used for either masers or lasers. The person that we're most excited about here at Columbia is Towns, who was in the physics department here for a long time, and then went on and looked at lasers and outer space. But in fact, Nikolai Basov and his colleague Prokhorov also played a very, very important role. The reason Basov's name appears here is because his son is now a professor at Columbia in the physics department. So you can see how things sort of circulate around in the same sort of area. Prokhorov's son isn't here, as far as I know, or daughter. Now, the people that were involved at the time I began to do entry were people such as I've shown here. First and foremost was Ali Javan. He was a professor at MIT. He had been here and then went to Bell Labs, where he invented the first gas laser, which sounds, well, maybe there's all kinds of lasers. No, there wasn't. This was about the second one, and he conceived of how you prepare the atomic levels so that you actually have a gain in that. Ali Javan's an interesting person because he had no degrees in Iran. He was just known as a really smart guy. And he came to the United States and he wrote a thesis in the physics department. And I was told when I was young that all it was one paper stapled in there. And I went and looked, and it's true. There's just one paper in it. Okay. The other two people here are very important in that they played major roles in laser techniques in the United States. Tom Deutsch, right here, had a huge role in CO2 lasers. Abraham Circa was very much involved in the detailed level structure of laser medium. The one on the picture on the bottom is very interesting because it is a picture of 1965 Columbia EE department, Electrical Engineering Department. And the person right here is a guy named Steve Bruick, who graduated that year and has been an incredibly prolific person in the area of quantum electronics, as we'll see going through my talk, okay? So the young students work with the older people to make real progress. I just noticed yesterday that Tom Deutsch, was the recipient, or not recipient, but the name of an inaugural fellow from the OSA department for biomedical applications. So Tom actually started very much this whole area of medical physics. He didn't do the whole thing, but he played a very, very big role in that and was very famous after that. Okay, so let's now look at this first application, or this first concept up here, ultra-fast power at a distance. And you can see when this is sort of 66 is about when I started here, and it sort of began to roll off in the 1980s, although it's certainly not completely rolled off, as you can see right here. So power at a distance means a lot of different things. But in this case, this is a picture of high-power laser applied at a distance, and so this is probably a fiber laser that's in there in a resonator. So what does this all mean for people who haven't seen anything like this before? This means that high-power lasers and shooting things at long distances was an initial driver of a lot of the research in the United States in the area of lasers. You're saying, well, that's terrible. Why didn't they put it into something else? They didn't, because that was an area that was of a lot of interest to people at the time. And so this played an enormous role in driving the development of a large number of lasers over time. But you say, shouldn't these guys have just done it on their own? No, they couldn't do it on their own. They had to have support for it. So this is a good example of a national objective actually driving the development of things. Okay, so I'd like to use a couple of examples of my own. And let's start with vibrational. Most of the initial high-power lasers were vibrational lasers. So typically these were in the infrared, and so this is in the thermal energy region of the spectrum, okay? And it uses simple molecular degrees of freedom. Okay, so what do I mean by that? Well, a diatomic molecule, even a simple diatomic molecule, vibrates up and down like this along the intermolecular axis, and each vibration level can be quantized. Okay, so this shows a sort of a quantized level right here. CO2, which is a triatomic molecule, has much more complicated level structure, has 3 eigenmodes that are characteristic of it. So to make a laser out of this requires that you have, let's say, a set of levels which are pumped. See, this is energy here, and these are 2 quantum levels. These levels are populated, perhaps so that this is very highly populated, and it transfers energy into another level of, let's say, another species of gas nearby. Okay? The most spectacular example of this was the CO2 laser, which was at the time I was beginning in the Air Force, a major laser for doing high energy applications, high power applications. By the way, a lot of work was done in looking at laser damage or looking at laser welding and cutting after that. So we had a different idea, which was that instead of using 2 different molecules right here, what we would do is use the fact that these vibrational levels change their spacing slightly as they go up in the vibrational quantum number. And when they do, they tend to pump each other up. See, the energy tends to flow up if this is done at liquid nitrogen temperature, as it's seen right here. So and it turned out to be a spectacular laser. It was like 1 kilowatt, 50% efficiency. That's fantastic. And it still persists now in many spectroscopic applications. Interesting thing about this is you'll notice there's a lot of simple things here, and it's not just me, okay? It's the fact that, notice the laser itself here is, you can't see it very well, but it's a glass tube, and it's covered with a black insulating foam that you cut and pour liquid nitrogen in. Okay, so this was all done by handwork by me with a blade, X-Acto blade, cutting this open and cooling this laser down to liquid nitrogen temperatures and making it work. And when you did, the results were spectacular. And this is the first paper we wrote on it with my colleague Bill Eppers out at Wright-Patterson Air Force Base. Notice, by the way, there's another distinctive difference between myself and Armstrong here. I had a tie on there, but I don't have a tie on now, okay? So maybe I've learned something, I don't know. Okay, now, those were lasers that were a very simple application. You know, go long distance, have a lot of power. But people also wanted to do other things with more or less high power lasers. One of these was to generate 16 micron light, that's in the infrared again, and to actually dissociate a molecule, in this case with an important isotope in it. In this case, it's uranium. So this whole isotope separation was done by absorbing multiple photons into a species such as that, and then blowing off the fluorines from that. By the way, this was of interest to the Soviet Union, which was there at the time, as well as the United States. And it applied to other isotopes other than uranium. So it's an efficient isotope separation scheme. There was only one problem with this. There was no 16 micron laser. And people looked all over the place for it. And then an important idea came along. Vibrational wavelength conversion by pumping a laser with another laser and using it as a device to convert from one wavelength to another. And you see this right here. Here's HBr, which is another diatomic molecule. It's a more complicated one than nitrogen. And it collides with the CO2 molecule. Here are these CO2 vibrational degrees of freedom, these little numbers written on here. And it transferred the population down. This was quickly switched on, and light would come out at 16 or 14 microns from that. And this 16 microns was exactly what was needed, and we could get fairly high power from that. So the point here was understanding the vibrational kinetics in physics was needed. So why did I stick this line in? Because of the fact is I told you that basic science and technology tended to flow together at that time. Professor Yardley, for example, in the audience, was very interested in CO laser spectroscopy at the time. And this was part of the whole idea of basic science, okay? Okay, there's other things that come up when you begin to explore scientifically. This is a picture here of liquid nitrogen. So this stuff you see in the halls, you know, the cans. This is an infrared spectrum transmission of liquid nitrogen. And you see that there's this very strong, what appears to be a band there. That band is due to the fact that the nitrogen molecules collide with each other and actually induce a dipole into an otherwise homopolar molecule. If you put CO in there, you actually create this other level, which is, it should be down a little bit from that nitrogen, and so you can actually transfer energy into this probe molecule, which then fluoresces. Okay? Now, the interesting thing about this is if you measure this probe molecule versus concentration, you find out that the molecule of nitrogen vibrates for 1 minute in liquid nitrogen. That's sort of an amazing thing. You excite a molecule in nitrogen and it vibrates for 1 minute. Wow, that's a long time. And I found that to be very interesting. And other people came up with other ideas. Steve and I came up with another one. We noticed that the spectra were very narrow. So you could separate isotopes here from each other. And I can't even read the isotope. Yes, I guess it's SF6 here. I'm sorry, I can't see it very well. But this is SF6, and you can see this normally you wouldn't be able to resolve that band at all. It's kind of blobby. But when you stick it in liquid nitrogen, you get these beautiful sharp features due to motional narrowing in that. So it's a potential new application to laser isotope separation. Steve and I patented it. The guy turned it down. We patented it again. He turned it down again, and he said, the molecule isn't right or something. And then we said back, then we decided we were going to just argue on his term. And we said, yes, it is right. And so we argued against it, and we made a lot of dough off that. I think it was $2. Okay. But we succeeded. And by the way, the idea would be to excite it vibrationally and then, let's say, kick it off by some ions or electrons or something like that. Okay, so another interesting thing is to understand a little bit about scientists and science at that time. So here's a picture of a whole bunch of people that were at this conference in laser chemical physics, which Javon had been one of the starters in that area. Bradley Moore had been another. So this is a conference which is held up in New Hampshire. Many of you may not know that. It's called the Gordon Conference. So you go there, you enjoy yourself in the Gordon Conference, go swimming, talk to your friends in the afternoon, and then listen in the morning and night. Jingwan Chen has been to a zillion of them as well. And I wanted to pick out some people here. So here's George Flynn, our well-known chemical physicist in the chemistry department, who's now retired. Here's another person. This is Eric Ippen. He's an EE guy in MIT. This is Chuck Shank. He's a physics person and maybe an applied physics person, I guess I would call him, at Berkeley. Here's me in Brook, and here's, I think, Lou Bruce right there, from what I see. So the point is, that's a pretty heterogeneous mixture of scientists. It's not just one type. That's all different types of people who've got different ideas for different reasons, and you can learn a lot from that. So my take-home message is departments are incredibly important, but you've got to look beyond them for some research. Now, as time went on, we were talking about lasers shooting at a distance. You need mirrors to do that. And then somebody just made a grand discovery. If you're going to focus down a 10 micron laser, which is in the infrared, you need to have a mirror which is 100 times bigger than if you have a visible laser. And so all of a sudden people stopped looking so much at the infrared and began to look at visible lasers. And you're saying that can't be so true. That's a simple argument. Yeah, it was, but it's true, what I just said. And so here are different kinds, solid state UV lasers, different kinds of photodissociation, excimer lasers. This was a laser which had only an upper level and no lower level, and therefore there was always a population inversion in it. This one turned out to be enormously valuable, but not as a laser weapon, but as an incredibly important industrial tool, as we'll find out in a minute, including ones very important for EE people. This is another laser based upon using cad sulfide, which was sliced up into little squares, and you could use an electron beam to excite it. And this laser was used by MIT Lincoln Laboratory to try to make a demo for interspace communication using deep UV light. They weren't going to use cad sulfide, but something else. But the reason I also put it up here is because Our original Bassoff that was up here, Professor Bassoff the first, was actually the one who started this all off, and we began to look at that. So that's another example of moving around in that same envelope. By the way, the work on that was done by Frank Tong, who's now a very rich person in China. Okay, so he went and became a professor in Hong Kong and then went over to China. Okay, now I put down almost all early laser research was seeded by the DoD. Very important point, because most people think, well, it was done by companies. It's not. So most of it was done by the Defense Department. And the first application, of course, was in high-power lasers. And I put this one up here, but that's not really a particularly good. It's a nice picture, but it's not particularly a great shot. But then it turned out there were a lot of other applications. And I mentioned laser welding of autos. And I mentioned an interesting thing. I went to a conference in Japan in the 90s. And the thing that struck me the most was the number of people from the former Soviet Union who were there trying to learn about lasers, not as lasers for weapons, but lasers for automobile welding. And they were the very same people, which switched over. And I found that to be an extraordinarily interesting thing. And by the way, laser welding for cars is an extremely important technology, which is worth about 3 or 4 of these talks. There's other things. I noticed this recently. This is an idea of using LiDAR, laser radar, to look down through foliage. And the application here was archaeology, mapping of a Mayan city. Idea is you have a pulse laser, maybe a pulse detector, and you can actually see underneath foliage that way. So that was, if anybody wants to ask a question, please do. Here's the one that really makes your heart warm up. Initially, there was a lot of work on ion lasers. Gwen and I were talking about that earlier today. Steve Halstead was a good person at that at Hughes. And the reason for this was as a night illuminator, to see things at night walking around. But as it turns out, the same technology was turned around and used for eye surgery. And this is laser cataract surgery, which I think a good friend of mine, Antonio Sanchez, had just a couple years ago. So this is a major factory whose probably product costs and everything way overwhelms the initial exploration and research in that area. Okay, so let's go beyond that. Let's now take a look at the rise of ultra-compact integrated electronics and photonics. And this is an interesting story in itself. Before I go into people right here, when I was at Lincoln and things were going beyond visible lasers, I began to think what would be sort of an interesting way to do. And I happened to see a Physics Today article, a Physics Today issue, which had an article in it by Ed Wolf, who was at Cornell at the time. And Ed Wolf had written this article in which this was either the title or an important quote in it that said there's plenty of room at the bottom. And the whole idea was people were thinking of fabricating things, but they hadn't realized that there's a lot of basic and really exciting physics and understanding and technological challenges in actually doing research on microfabrication. It's a really rich and valuable thing. And so myself, Tom Deutsch, and Dan Ehrlich actually sat down and began to think about that, and we realized that lasers in microfabrication can become important, and furthermore, surfaces played a huge role in controlling the properties of that. So let's just take a look at a couple examples here. So one of our initial things was we took dimethyl cadmium, not a nice gas, by the way, not a nice gas, but we took it, we put it in, we focused an ion laser through there that was a doubled argon laser, and it turned out that when we did this and we looked at the substrate, we ended up with a bunch of things that almost look like Fresnel rings. And this is pure cadmium that was deposited right there. And the thing that's most exciting is not just the fact that you kind of create this optical structure there, but that the resolution in this is much smaller than a wavelength. So we were able to make very, very high resolution, which at the time was quite exciting because people were trying to get at resolutions of that order at that particular time. We weren't into nano yet. Other things were done. So Tom looked at tungsten deposition, interconnect deposition from tungsten hexafluoride using a 193 nanometer laser. That's an excimer laser. And what he did is he put it in the gas and then scanned a wafer down. The wafer is this thing that looks like almost a toilet seat here. And you scan it through there and you get this interconnect made of tungsten. Up here, a student that we had, Dan Ehrlich, and also a student here, Vic Trace, who's the lawyer now, actually wrote down a beautiful silicon interconnect on that. So this is something that starts to look pretty practical, this and that, because tungsten was used for solar cells and silicon interconnects were a common technique for integrated circuits. So they were practical materials. So the first thing we did, though, was to take a look where just adding metal was kind of interesting. And I had a friend of mine, Don Silversmith, which we were just talking about today. And Don Silversmith had suggested mask repair. So what we did is we put in a little break in this line, and we filled it up with dimethyl cadmium, but we could have used aluminum. In fact, we did in some cases. And this is it up here. Subsequently, Dan and Ken Nill, who's this gentleman right here, began to look at silicon interconnect repair, and they developed started a company called Revise. And Revise made a lot of dough for MIT, made a lot of dough for Lincoln Labs, and it made a little bit of money for me and for Ehrlich and for Tom Deutsch. Dan Ehrlich, Tom Deutsch. Ken Nill was an entrepreneur who worked a lot with Lincoln and startups from that company. And so that's an important point, is it's good to know entrepreneurs who are around there who can actually work with you on startups. Finally, we decided to do a few other things. For example, we knew that lithography was important and exciting. So Hank Smith, who is a fabrication professor, very known fabrication professor at MIT, that doesn't mean everybody leave. Don't leave. Okay, so what Hank was interested in was using the 193 nanometer tool, which is an excimer laser, to actually make closely spaced grading lines. And what he found out is if you make a phase plate up here, and if you look going away from the phase plate, you can actually do a spatial period doubling of this due to in a certain kind of resist, PMMA. Well, that's an interesting thing you say, and whoopee-doo. Well, it turned out the whoopee-doo was that it turned into the main fabrication, the main lithography tool, and I believe it dominates the lithography market right now in the United States at 193 nanometer. This thing funded a huge program out of Lincoln for many years to develop the technology, but it was also very, very important just as a major commercial tool. So it's made money way out beyond the original money from that. The Japanese also got very active in that as well. Okay, and this was, I haven't done a very good job, but this was all done with DARPA funding there. In fact, all the programs I've talked about before have been funded by DoD. Now, there are questions that you might ask which are more basic, okay? So some of the basic science questions is, okay, so we've talked about lasers doing things on surfaces. What exactly does it do? You know, light hits a molecule somehow and something happens. It's sort of an interesting thing, but what's it mean? So the questions to ask is, when you have a molecule on the surface, so let's use this methyl bromide as an example, and you irradiate it with light, does it cleave the bond there due to the light, or do electrons come out of the substrate? And what happens if you have a spacer layer in here? Okay, so this is a really important question which can control eventual applications of this as well. So what we did is up here on the 13th floor of the Mudd building, we built a time of flight system. So this is a mass spec, and we irradiated it with a pulse laser, and you could see several clear velocity peaks, direct on electron or photon bond cleavage. You could see spin orbit splitting in some of the fragments, and you could understand coverage dependence. So this is an important way of coming up with new ideas for changing the properties of a surface. And in fact, this was also, this work here was funded by a long-term DOE program I had from a guy named Al Laufer, which George was funded by, and many other people in the chemistry department. At the very beginning, I was very interested also in the fact that you have light on the surface. You might be able to actually do some surface chemistry on there, and you might see resonant features due to it. So at the time, I don't have the right manuscript right here for this, but yeah, here it is. Julian Chen and myself, Julian's again right over here, and we were looking at the idea of exciting nanoplasma resonances in this feature. So little spheres of metal, of like 100 nanometers or so, actually it can be excited. The electrons in there can be excited, and you can actually generate a large absorption within the material. And it turns out that these metal spheres, which you see here as black, actually grow into elliptical long features here due to plasma-induced chemistry. Interestingly enough, that whole idea was forgotten. And then maybe 3 years, or about 5 years later, it was rediscovered, 5 years from today, was rediscovered in Germany. And this points out that in science there are many cyclical rediscoveries. It's a continuing thing of people discovering something and then rediscovering it. And I don't think it's bad, I think it's good, but it's sort of an interesting way that how science proceeds. We also discovered that if you just let the light shine through a cell, in a vacuum cell containing the dimethyl cadmium gas, you got this very highly structured surface here. You see these little fringes. That's an interesting one. This was funded by DARPA, by the way. And what you see is that you get this grating thing formed. And the grating forms because of the fact that when you let the light on it, it starts to create little scattering centers. Those scattering centers create plasmons, which go along the surface of the metal. And if they hit the right wavelength, you get feedback, and you can actually make light sculpturing from that. And the whole idea of using light sculpturing turned out to be very important, not necessarily in metal applications, but in polymer applications, and some beautiful work has been done in that in Germany in the years. But I think that's a very nice way to sort of begin it. Tom Deutsch got very interested again in solar. I guess he was a environmentally sensitive man at his distinguished age at that point. And so he decided that you could take the same structure that we talked about for the tungsten interconnect and you could do sort of nano melting of the surface. You would heat the surface very, very quickly with an excimer laser, and then you could make a very high doping content in that surface layer. This is aluminum that's doped into that, and you can see there's a really drop-off. This is depth. This is the aluminum concentration here, and you can see it drops off quickly. And this eventually started a company that had this process termed gilding, and it was done at Stanford by a guy named Tom Sigman, who did this, and it actually was sold, I think, commercially quite a bit for making really highly doped PN junctions. Finally, and we'll move on, one of the areas that we started to talk about was electron chemistry. Remember I said electrons could come out of the surface? So we decided that maybe you could kind of make a use chlorine on a surface, you irradiate it, and then electrons would come out and be captured by the chlorine and dissociated. So we made a structure here, which you see, and a process flow, and then we worked with Professor Wang, who actually had some beautiful material right here, and we actually etched a beautiful laser right here by one of Wen's students and some of the guys working with me. And this was an example of cryo-etching, a wholly different thing. In particular, this structure didn't go anywhere, but cryo-etching did in the United States as a commercial method. Okay, so that's sort of the first part of this second area. Another one is modern metal optics. Can useful photonic structures be made which are much smaller than a wavelength? Okay? So that's the question that we're going to look. Why do we ask that question? Because metals are very simple material, so we can do elementary nanofabrication, but very small distances in that. In principle, you need about 10 to 100 nanometers in size. Plasmons have about the right wavelength, so maybe we can use them. There's some exotic applications, which we'll talk about in a minute. But the question is, can these structures actually been made, and what are their properties? Okay? So here you have the ability to make really tiny features, and you could go on doing fabrication research, or you might ask, what can we make with them, and can we get people excited in them, in those things that we make? Okay, so you can make it. Here's an E-beam, which was done, I think this was a SEM writer that was out at Brookhaven at the time, and we made very high resolution little crosses right here. But while these are very good and they show you can etch, they're not big enough for some of the applications that we need. You can't get the field you need because of the fact that you have to stay coherent over a long distance. Another question is supposing you do make things, can you actually probe them? Okay, I'm not going to explain all of this, but what I am pointing out is that you can use ultra-fast femtosecond photo emission to actually play with electrons at surfaces. So here we take out an electron and then we probe it with a second light and actually see it. So this is all done with a femtosecond Ti-Sapphire laser in ultra-high vacuum, so that's like 10 to the minus 12 or so torr, very low pressure, and it's complicated, but it's ultra-fast and extremely practical, and you can really follow individual electron motion with that. So in the midst of this, there was a lot of interest in one idea, negative refractive index. Okay? Negative refractive index. Some people call it left-handed materials. Okay? The question is, what does this all mean? Well, you know, with Snell's law, you get light bent in a certain direction when you go through go from air into a piece of glass. With a negative one, it bends the wrong way, bends another way. And with a property such as this, you can show that if you have such a material, you can actually make very highly resolved features. Now, people have shown in the meantime that maybe it's not so easy to do, but basically you can do it, okay? And there's other applications as well, which we'll mention. But, so the question is, you know, can you make these things at all? So the first thing to do is just take some very good simulation tools. And so this is the first example of where simulation turns out to be really important. The idea here was, can you actually simulate one of these negative materials? So here we had straight lines, straight metal lines. We had split ring cylinders right here. And you can make permittivity and permeability less than 0 with that, and that makes a negative index of refraction. So here's an example of that. So that got people excited. You can do it at visible wavelengths. There was beautiful stuff I point out in San Diego by Schultz and Smith, who actually showed you could get it at microwave frequencies. But here was a suggestion that the physics at very short wavelengths allowed you to do it. Okay? So Steve and His colleague Zhang and Fan got together with us, and they had an interferometric lithography, so that's a much larger tool that you can use. And they showed that you could make a round type of structure here out of metal, and you could make these lines, or you could do it by actually making a planar version of that right here. So you can actually hope to make such a structure, it appeared, that would be a negative index of refraction at visible wavelengths, because nobody else had ever made that. A lot of talk about it, but nobody had done it. So Steve actually set this up at the University of New Mexico. We collaborated with him as doing the computational work, and you can see that the measured feature and the simulated feature are identical. So that means you can make negative index of material. It's high spatial resolution of light, and one of the applications is cloaking. So there's a huge program in cloaking that was done by Pendry, John Pendry, who was an Englishman who came up with all of these ideas at the very beginning, and an incredible effort that lasted many, many years. And it's used a lot in cloaking. You have a plane. You can't see the plane because the light bends right at the plane surface. There's other things you could make. This actually shows a diffraction grating, which is, you can't see it, but it's a circle. So it's a circular grating. And what it's used to do is light comes down, scatters in the grating, and half the light moves forward, goes in, and it's captured by the substrate, which has a detector in it, an infrared detector in it. So it actually moves in, is captured by the detector, can be very small, and you can get a huge enhancement in the absorption as well as a large enhancement in the signal to noise out of this thing. And again, this thing was a simple enough device that there was actually a startup in that area that was brought up, I think, by Steve and his group. Okay, nanostructure and nonlinear optics. So the question is, we've talked about visible, we've talked about light, but it's been more or less linear types of behavior, not nonlinear behaves. And I thought I'd just stick in one comment on my advisor right here. This is Ali Javan, much later in life from when you first saw him. And he had a project at MIT Lincoln, MIT, not Lincoln, but MIT, in which he looked at optical frequency mixing in point contact diodes. So this was, the idea here is, can you mix a far infrared light with a visible light, like a helium neon laser? Can you do that? I mean, that's a tremendous thing. And from that, can you learn basic information about speed of light and other relevant fundamental questions? So this was an example of nano before nano, because the peaks here are very small. It was DoD funded. Ali had a lot of money to begin with in that area. But again, you can use simulation to get insights into this. This is looking at a nonlinear effect here using finite difference time domains done at Columbia here by Nick Pinoyo and Ryan Roth. And what we found out was that you could do beautiful simulations of the light of Raman scattering on the surface right here. And it took a lot of work to do it and to get it right, but it worked. And it really is, it shows you how powerful the simulation tools have become now, where you can really learn things really beautifully before you actually build them. That didn't exist for these tiny things until fairly recently. Okay, now let's spin off a little bit more recently. This is 1980 to the present. I came here in 1980. Present is now. Dimensions even smaller. That's maybe 1995. Maybe I'm pushing that a little bit. Maybe it's 2000 to the present. And let's look first at information, bandwidth information, and data. So what we're talking about here is integrated structures. So the person that needs to stand up and bow is Professor Wilner, who's right here. This is his name. And Professor Wilner actually worked in this project. And the project here was, it was a heterostructure of gallium arsenide on top of aluminum gallium arsenide. And what you would do is put two little notches in here, and by controlling the notches in it, you actually can make a waveguide, and you can write a waveguide all over the surface. It's a direct write method that you can write all over the place. And it worked very well. Obviously, I faked the golden egg here, but it's I didn't have the one with the picture in it, but actually you could see it under infrared light. But it was a beautiful thing, worked very, very nicely. Herman House had a lot of ideas for that as time went on. And again, this was DARPA AF4SR funding thing. Notice Dan Blumenthal, he's a professor now out at UCSB. And Dragon became a manager in, I don't know, applied materials, I think it was. Mark's a patent person in Israel, and he was head of the IBM lab there. So you see what happens to people over time. Okay, now I think one of the most exciting areas is of silicon photonics, waveguides in silicon. It really was conceived, I think, as a general concept by Richard Soroff. And he did a lot of Richard was a program manager, or maybe not, a scientist is a better word for it, in AF4SR, Air Force Office of Scientific Research. And he explored a lot about making structures out of silicon. Then Bahram Jalali, who's a Columbia graduate, in our department, or was he our department, was it applied physics? I think it may have been applied physics. But he was also in our department in reality. I mean, he came up here a lot and had his apparatus up here a lot. Is that right, Alan? Yeah. And and he looked at the idea of taking CMOS types of materials and chips and actually building a silicon photonic and making certain kinds of devices. And this was a really exciting one. He gave a lot of talks, and it was actually bought out from UCLA by Intel, and he made a lot of cash on that. Okay, so he became wealthy, I think the word is. Okay. Then there's a realization in higher contrast materials, and a bunch of people at MIT, including Professor Lipson, who was at MIT at the time, and others, and myself here, started to look at SOI rather, and that has very high contrast of the index of refraction of silicon on top of a layer of SiO2. And with this, you can build tremendous number of things. Optical rings all over the place. Alex, you've done rings everywhere, and Professor Lipson as well. High bandwidth interconnects, nonlinear sources, coders, etc. Okay, very, very rich area because you can begin to use standard fabrication tools, and I think my friend Popovich up at MIT had a bunch of papers in that area which are beautiful. So this just illustrates one. This was done with Ben Lee, Oliver Chen, myself, Karen, and I think Professor Vlasov at IBM was involved in this. And basically this is putting light through a silicon wire. So this is really tiny. See the dimensions here? They're very small, 360 by 220 nanometers. And you can see that you can put a lot of information through there. In fact, the paper made an argument of 1.28 terabits. I think the referee argued a little bit, but not too much. Okay? So that's pretty much it. It is 32 wavelengths, 40 gigahertz, 5 centimeter wide silicon waveguide. That's an attractive thing to know about a very high bandwidth interconnect. We went on and looked at other things. So here's some structures done at B&L. So this B&L has a beautiful E-beam writer, which I've used a lot. It's fantastic. Here's SiO2, by the way, with the SiO2 silicon and the substrate. This is used for a lot of silicon wear, but there's other kinds of stuff which are more bulk-like silicon, and there's techniques for working with that as well. Okay, so in this case, we looked at asymmetric Ys for mode division multiplexing. In other words, Here you're using wavelength for one channel and another wavelength for another channel. Here you're actually using modes, one channel and then another channel. And so you might come in, something happens in the middle here, which is determined by the circuit you're trying to make, and then goes out, and you can put information and identify them by modes. In our case, I think there were 2 there. And here's actually some measurements. They're very good bit error rate measurements on there. And you can see the crosstalk is excellent. The power penalty is quite good too. So this was beautiful work, and with those are eye openings in that thing. And that came out that was done by Jeff Driscoll, who's now at Intel, and Christine Chen began to work with him, and Rich Grote, who's at JPL. Christine's also at Intel. Just recently, we decided to look at a demodulator. So this is the DPSK, what is a differential phase shift key demodulator. In other words, you have a signal which has got this phase on it, and it's used for communications. And here we have a 10 gig one and a 20 gigahertz one over here. They each have delay lines. This is a longer delay line than, a shorter delay line than here. And what we have up here is sort of a close-up of that, and it works beautifully. Okay, this was done with Karen Bergman also. Wanted to make a point of that in her group as well. We had some collaboration with people at West Point and PSI, which is a small company in the Boston area. This actually shows another important idea. This is one of can we do nonlinear stuff with these silicon wires, just like we talked about nonlinear stuff with the other kinds of integrated optics. And in this case, the idea is, how does this is a pretty active and exciting kind of fiber because it has a huge nonlinearity compared to, there it is, compared to a silicon one. And it has a nice GVD coefficient. And as a result, we can work with a very short wavelength as opposed to, let's say, a kilometer right over here. And you can move it around a little bit depending on what you want to do. So this has the concept I came up with on this one was it's a fiber on a chip. And again, Alex has worked in this area as well. And so you see strong enhanced nonlinearity. Dispersion allows silicon wires to have a fiber optic response on a chip. So you don't have any of the vibration which you get with a normal fiber. And you can get a very large scaling of this thing. By the way, I point out that something I didn't mention anything of, and I haven't done anything on it, but fibers and high power lasers are a crucial point to this power at a distance now. A lot of them are made with fiber lasers, okay, is the way that is done. So that's a huge technology which I wouldn't have dreamed of years ago, that you can make such powerful and useful things as that. Another application is 4-wave mixing. I won't go into this too much, but this is the short, this is a butt end of a silicon waveguide right here. We're surrounded by some nitride. And with 4-wave mixing, you put in, this is a degenerate one, so you have two photons of one type. Then you have a signal and an idler. And you can actually tune your signal and vary get amplification across the band of where you would like to be. In this case, the reason we did this is because we worked at mid-IR, 2 microns, and so you don't have to worry about the idea of 2-photon absorption, which does hurt you if you use the 1.5 standard telecom thing. So this is used at 2.2 micron. I wanted to point out this is work that we did with IBM, so they played a very important role. Xiaoping Liu did that. Okay, so let me wrap this up by saying right now we're looking a lot at making the dimensions even smaller. Now, I shouldn't say we. I think the country is interested in doing this. So this means you have a waveguide. You can't squeeze it laterally anymore, but what you can do is maybe reduce the height of the waveguide. Okay? So this is an area which runs a lot into surface condensed matter physics. It's a work which Columbia was very strong in. We got a number of different big programs in that area. So that was Philip Kim, Abhai, Professor Heinz, Ken Shepard, myself, and several others, Corey Dean. It worked out beautifully. Now, what are 2D materials? These are two-dimensional materials. They're thinner and smaller and smaller and smaller, and then they're only atoms. So it's like one monolayer thick. I like to show this one because I thought maybe Jingwon Chen would come in, and so I wanted to show that you can make catalysts with this and you can strain tune it. So this is work that I did with Dennis Potapenko down in the basement a couple years ago. And it was funded by DOE Basic Energy Science. Okay, so there's been a lot of excitement about very small nano object. One of the most important issues is what's the electronic structure in, over large bands, and mostly it hadn't been done because these little crystals are so small that you can't use a normal kind of electronic structure to understand that. You have to probe it with a very focused light. It's a major U.S. effort with large groups and major instrumentation to measure at atomic scales. A lot of buckos. It's expensive. Okay? So let's take a look at some of this instrumentation right here. This is Brookhaven National Lab, and a shockingly large number of people in the audience here have never been to Brookhaven National Lab. I just say that, but I think I'm right, okay? You should go. And it's easy to collaborate with the people because they have instrumentation set up. I mean, they have groups that are set up there whose purpose is you get people to collaborate with you or you don't get any money. So I said that a little too harshly, but that's basically the idea. They want to have collaborators. So we've done a lot of work with Jurek Sadowski and with Peter Johnson and many others looking at synchrotron uses, STM, scanning tunneling microscope applications, and other things as well, okay? So let's talk a little bit about this. Computationally, it's very complex. There are advanced tools. We've told about these are the centers nearby that you can do collaborations with on it. But you can also work with people in different departments, that's as well. Okay, so here's a picture of an important item, which is a set of bands. Notice this is thickness, so this is 1 monolayer, 2 monolayer, 3 monolayer, 4 monolayer. Notice the band here changes. So this is the peak of at the gamma point, and this is the K point right here. And notice that as the thickness increases, the gamma point goes up and the K point goes down, and it keeps on going. Okay? It does that because of the interaction between the layers of the different materials. Okay, so this is done with a device called a spleen, which has a very focused, sharp device to allow you to look at 1 micron samples. So they're very tiny. You can look at thickness-dependent position, the valence band maximum. By the way, this type of shift here means that it goes from a direct band gap at 1 monolayer to an indirect band gap as you go to the second monolayer and beyond. So there's actually some beautiful pictures that were taken in Professor Heinz's group, which show that you have a bright object at 1 monolayer and you go to 2 monolayers and you can't see it. Or you can see it, but it's much harder to see. Okay? So new devices, maybe this means new devices, new materials. There's another idea right here, which is that this shows a sample which has 2 layers in it, this greenish one and the brown one. And the idea is that you actually take these off and put them together. So this is not beautiful grown MBE material such as Professor Wang grows. This is just hand sticking 2 samples together. So Professor Hone is an expert in this, and I should have mentioned his name earlier, but I'll just mention it right there. And what you can do is look at the orientation of these layers depending where you want to put them, so that you see this kind of moves around here. And you can see that the band positions actually change as you change the angle. So what does this mean? Well, you can publish very nice papers. You can learn some interesting physics of it, that's for sure. Can you make real devices out of that? People are looking at it right now. I would say that it's going to be a little bit hard, but I have an open mind on it, okay, to do that. By the way, I missed one thing, which I think I'm just going to go back to show you, and it's just a second. You notice right here these straight lines. These indicate that you can actually, this is a stepped copper surface, and you can actually make very, very skinny cobalt wires on this by cutting the wafer at an angle. And it shows that it's possible to make really, truly nanostructures when you go through this. Okay, let's go back. And finally, let me just point out, this is my research group not too long ago. So here's the big banana right here. Here's Svetlana right here, who's been working very, very hard. Here's Jerry, Jeff, Alex Meng, who's right here as well. Zhejiang, Stan Wong, these are all people you knew. Peter just got his thesis today, not from me, but from John Kamissis. Nader works out at Brookhaven. Brian's in the Pentagon. Rich is out at JPL, and Dennis is over at Princeton. Somehow I think Princeton's the best place, but I don't know. Now, I could not have done that without many friends, so I had to make a slice here. Some friends aren't on. I'm sorry. Some friends are. They're happy. So here's Antonio Sanchez, who did the electron beam work with me. Irving kept me from going nuts, and he deserves the most work of all. He completely keeps me from going loony every day, so I appreciate him a lot. Jerry also does the same thing. Here's Steve Broerk, who worked with us a lot. Gary Carter on different fiber optics, and Harold Fetterman, who was an old colleague back at Lincoln, who's just a very, very good guy and became famous for Schottky barriers, which he invented when he was there. Now, I just wanted to point out that Alan's a special person. And I was out there walking around, and I came across this guy on a horse, and it's Alan. I discovered it was Alan right here, and I asked the question, will Alan never stop? And it's true. He just keeps on going and going and delivering and delivering. And there is a photo credit here, I have to admit. Okay. So that's my one joke. Okay. But there, of course, is one super friend. Here's the real friend that never stops. Mrs. Osgood, who's not only lovely, but very smart. She got first in her class in Winchester High School years and years ago. And she is one super dude. Notice the gold coming out of there. Okay, so what have I learned? I've learned science and engineering go hand in hand. I think this business of science, oh, he's doing science, it's baloney. I think that things go hand in hand. You've got to keep an open mind. Without DOD and DOE, I think you'd be really hard-pressed to have research. DOD provides huge amounts of money, and it's one of the few ones that does it. Same thing with DOE. Friends are crucial. With no friends, you really are limited, and then you have to look beyond department walls. At lunchtime today, I had Abhay Pasupathy. Abhay, are you here? I don't know whether he is, but, oh, good. Over there, okay. Abhay has done a couple papers with me, and I've learned enormously amount from that. It's fantastic. And Mark Hybertson and I recently at Brookhaven have done a lot together. It's a wonderful thing. I also want to thank these particular people for funding over the years. Many people know Don Silversmith. He was, again, a subject of discussion today. and Gernot Pomrenka, Howie Schlossberg, Charles Ng, Dick Reynolds, maybe Harold Weinstock should be on there too. But those are ones that are particularly long-lived. And then finally, this is it, the group and time. Okay, this is the next day I told them, it's the end, baby, I'm pulling the plug. Okay, so that's when it ended. Okay, thank you very much. Any einige Frage, bitte. Yeah, any questions?
Great.
Yes.
For the monolayer TiO2, I'm really intrigued. So you can tune the string in the example which was on the gold, right?
Yeah.
Can you put them on copper, nickel, any other metals?
Let's see. I think we concentrated on gold, but we have looked a little bit at some other materials, I think. Dennis is the big expert on that, but we've also looked at different structures. Those are obviously single crystal settlements. And we wrote a paper just on reaction versus strain. So it's a very nice thing. This is done with STM work, by the way. Jing Wang, by the way, does a lot of the same kind of surface science. There's now, what, 3 of us? You and Xiaoyan Zhu and myself and Abhai have all done surface science, so we're in much better shape than we were years ago. Okay? Any other questions? Yes, Mike.
A big part of your talk was the relationship between the researchers, university,
Yeah.
and the government sponsor. And your career spanned this time where government sponsorship of science is increasing for most of the time. How do you look at the future, next 10 years, next 20 years? How are things looking with the funding for research? Like what you experienced here?
Well, there's a funny thing, right? This year was supposed to be a terrible year, horrible. The budget was zero. Man, everybody hated it. Turned out in the end, it was a slight cut, but not a big cut. I think in the end, most representatives and most senators, not all, but most of them really, really like science. And they're particularly enamored if they see it's going to do something useful in the end. And they also like it if it's not generating intellectual property that prevents industry from using it. So I think my own feeling is that the universities don't do a good enough job of making their point very clear what happens. But so I think it's going to, I don't know if it'll grow giant, but it's going to do pretty well. I mean, the other thing to note about for people who are not here is that there are other programs which are very, very important. And how do you decide which program gets which and which doesn't get the other? And, sometimes you can just jack things up, sometimes you can't. So that's my feeling about that. Yes, Mikhail.
What do you, for a young assistant professor, say that just started in optics?
Is that me?
Sure, you would be. In optics-related area. Well, what would you recommend in terms of research, in terms of general advice, but also in terms of research area? Where would you?
Well, I don't know. I mean, here's one thing. So let me just give you part answers, okay? One is, we got a huge medical school, right? So, man, we want to all go for medical. I don't know. I'm not so nuts about that. I think the advancements that we can make, if you look over the years, are stand alone, and then they get applied to medicine. So I think that's the big way to do it. Synchrotron, which it turned out was used for structural biology. Let me just mention something. There was a huge market for the synchrotrons for structural biology because they could look at big molecules. They had beautiful light and everything. It was great, and it still is great. But who developed it? It wasn't structural biology people. It was done by DOE people. And that goes around a lot. These things come from hard applications which get done Or another one is, what is it, limited distance tomography, you know, that Fujimoto does. You know, I think it came from probably some DoD program that Eric Ippen and those guys had. So I think what you should do is find hard optical problems which you can have a vision in. Nungfang has done things like this, soldier ants and so forth, or maybe the ants aren't a good one, but the other things are that are good, the little features on the surface. Yeah. And so I think that's those are good things to look at. So I think if we just become an adjunct to the medical school, I don't think it's necessarily the best thing to do. There's been a couple of examples of that. One is WashU, where my brother's a law professor at, and WashU has a huge medical school, and it's been pretty darn successful. But they have a terrible time trying to get the other things off the ground. So that's a comment on that. Yes, E.
I have a question that is, as a junior researcher and as a PhD student, sometimes probably students professors, senior researchers, about, okay, how did you start your research? And why have you been devoting for decades? And many answers will be like this. Okay, for laser guys, they said, oh, it was a golden time for laser. And for STM guys, they said it was a golden time for STM. So what is the golden time for now? Maybe there's no such answer, but I want to know your comments. Also, I want to know, how to distinguish between golden time and the bubble?
I don't know, you got to look and see what the application is. Is it going to last for a couple of years or not? I don't know about the golden time thing. I would, I don't know. My feeling is that there's always new ideas that you can come up with, and you should work on those. The funding, it's always a problem, but that's part of the issue of what you have to do. You have to come up with ideas and to make and to present them properly. That's why Professor Lipson is a very good person. She knows how to present her ideas right? Maybe I do too, I don't know. But some of we do. You have to go out and talk to your program managers that exist. The laser chemistry stuff was supported by a guy named Dick Reynolds. He's passed away now. He used to be at Hughes Malibu, and then he went to DARPA, and he did that. So I knew him from several interactions that I had with him over the years. So getting out and talking to people is very, very important. And anyways, that's yeah.
Okay, let's
maybe one from a gentleman of similar age.
Can you comment on the bureaucracy we may have faced over the 50 years of your research, and how has that evolved?
It's gotten worse. That's why I had that nice thing for the administrators on the bottom of that slide, because it's just gotten worse and worse and worse. And I think you have to fight back. I mean, and it's not you or me. We can't do it. But I think college administrations have got to make a case for themselves of why they have that, and they've got to deal with reality, you know. Okay, I won't say anymore. Thank you.